Welcome back to our course of trusses, and we have our subdivided truss, or sometimes called as Baltimore truss. This truss can be considered as an initial truss and several small triangular trusses inside this initial truss. There are two methods for computing this truss. The first is consider the full truss as it is shown and compute using traditional methods. The second method is to separate the initial truss from the subdivided trusses here or the triangular small trusses here. Let us first consider the first method, our full truss. We have our truss 1, 2, 3, 4 multiplied by 2. This makes 8 panels, each of 4 meters, making a total span of 32 meters. The truss is symmetric about the member 5, 4. And we have for each part of the symmetry a 10 tons on the upper chord and a 6 ton at an internal joint here. From symmetry, we can conclude that YA equal YB, each 16 tons. And we start computing our internal forces. We start by section S1, S1 as shown, and we extract the smaller or the easier part, which is the left part here. And we start considering our equilibrium equations. We first note that we have 3 unknowns, which are the unknowns in the members having the cut S1, S1. These are the members 1, 3, 8, 2, and 11, 2. We analyze 8, 2 into its main components, and we take sigma y equals 0. We choose the y direction first because this equation will have one unknown, which is the force in 8, 2. Of course, we would have taken a moment about joint 2, and therefore in this equation, the moment equation, we would be left with the only unknown force 1, 3. And therefore, we precisely repeat that there is no one method to start computing or to compute any internal force in a truss. So, going back to our equation, the equilibrium in the y direction equals 0. We have YA and we have the component of the force 8.2 in the y direction, which gives that F8.2 equals 22.63 tons, the tension force here. Now taking moments about the joint 1, we cross out the forces 1, 3 and 8, 2 as those two forces pass by the joint 1, and we have an equation with the only unknown 11, 12. Here is our equation, the force in 0. Sigma forces in the x direction equals 0. Now we can compute the force in the member 1, 3 to be minus 16 tons, the compression force. We go back to our truss and start our joint method. Starting with the joint 11, we already computed 11, 2 to be 0. Anyway, we extract our joint here, and we take sigma forces in the x direction equals 0. We have 11, 2 equals 0, previously computed, and from the equilibrium in the x direction, we conclude that 11, 2, that 11a equal also 0. And taking the forces in the y direction, we have the force in 11, 8 equals 0, as there are no other forces in equilibrium with it. Now we move to joint 8, and we extracted outside here. We already computed 811. 811 here equals 0, and therefore it doesn't really appear on our drawing. No need to have any zero forces here, just to simplify our drawing. And since the direction of the member 8A is perpendicular to the direction of the members 8.1 and 8.2, then we can consider that this direction is an x-axis and the perpendicular direction here, 8A, is the y-axis. To simplify our computations, instead of having too many analysis of members, and considering the force in this inclined x direction, we have that 8.1 equals 8.2 equals 22.63, as 8.2 is previously computed here to be of this value. And taking the forces in the y direction, we conclude that the force in member 8A equals 0, as there are no any other forces in this inclined y direction to be in equilibrium with it. We move to joint A. We extracted outside, and we recall that the force in A8 is already computed in the previous step to be 0. And taking forces in the y direction, we conclude that F1A equals minus 16 tons. Taking forces in the x direction, we conclude that A2 equals 0. Proceeding with our internal forces, we take another section, S2, S2, and we extract the left part here to get ready with our equilibrium equations. We analyze the force in 10.4 to its vertical and horizontal components, and we have all our angles here, our inclined angles, 45 degrees. Taking the equilibrium in the y direction, we get rid of the forces in 13.4 and 3.5, which is a very wise equation to start with, because now we have just one unknown, which is 10.4, in this equilibrium equation, and we compute it to be 0. Taking sigma moments about joint 3, we get rid of the forces 10.4 and 3.5 as both pass by the joint 3, and we are left with the only unknown F13.4. Always it's our aim to find equations that carry one unknown in it. So F13.4 equals 19 tons tension force, and taking sigma forces in the x direction now, we have 10.4 already known to be 0 and F13.4 already known to be 19 tons, and we are left with the only one unknown 3.5, so we can use this equation now. And this gives that the force in F3 equals minus 19 tons compression. So really having, to sum it up, really having a cross section in our truss, we have uncut members, means that we have n forces to appear in any equation of the three equilibrium equation. We choose an equation that makes us have one unknown in it. So if we have two components, say in the y direction, so it is a wise procedure to start with the perpendicular direction, x direction, if it carries one equation and one unknown, and vice versa. Or we choose a point, a joint, around which we take moments to cross out the unknowns and keep us left with one unknown in the equation. We proceed with our truss here, and we move to our joints to take joint 3, and we extract it here. We start with the equilibrium equation. Sigma forces in the x direction equals 0. Sigma forces in the x direction equals 0. F3, 5 appears in the equation, F3, 1, and the component of F3, 10. F3, 5 and F3, 1 are previously computed, and we are left with the force in 310 to be 4.24 tons attention force. Taking now the forces in the y direction equals 0, we can get that the force in 3,2 equals minus 13 tons. Now all the forces connected to joint 3 are known forces now. And we move to joint 10. We extract it here, and we analyze this 6 tons into the considered x and y inclined directions. Taking equilibrium in this y inclined direction gives that F10 2 equals minus 4.24 tons. Compression force. This concludes with our first method, computing the subdivided truss altogether as the traditional method.